Now we want to discuss how do we balance chemical equations. So balancing chemical equations comes from the fact that there is a conservation of mass. This is a law. So it's a physical law. So matter cannot be either gained or lost in the process of a chemical reaction. So if I have 5 grams of hydrogen, well, let me use a better example. So hydrogen has a mass, let's say, of 1 gram, right? And in water, in the formula H2O, we have 2 moles of hydrogen, so H2, that equals 2 grams. We have 1 oxygen, which equals 16 grams. So that has a total mass of 18 grams. So if I said in my chemical equation that we had 2 grams of hydrogen plus 16 grams of oxygen, that would produce 18 grams of oxygen because the mass is conserved. I have 18 grams over here and I have 18 grams over here. And that's what we mean by the conservation of mass. The mass has to be conserved through the reaction. So I need to make sure that I'm doing that. And the only way that I can do that is by balancing a chemical equation. So here, balancing the chemical equation, we have to understand that there is a number that goes in front, and that is called our coefficient. The coefficient is the only number that I can change. I cannot change any subscripts. So for example, let me rewrite this without the coefficients. If I had mercury oxide, mercury 2 oxide, decomposing into mercury plus oxygen, okay? If I started out with this equation and I was asking you, I need to balance this, okay? And you came over and you said, and you did this. Well, I have 1 mercury, I have 2 oxygens on this side of the equation. I have 1 mercury and I have 2 oxygens on this side of the equation. That's true, but what happened is I no longer have the correct compound. This is not what I started out with. I started out with mercury 2 oxide. Okay, I ended up with mercury 4 oxide because this would have to have a 4 positive charge. If this is a 2 positive because 2 negative here, this would be 4 minus due to the 2 oxygens. Okay, that's not what I have. I don't have mercury 4, I have mercury 2. So I have to keep this the way that it was. Okay, I can't manipulate subscripts. Subscripts have to stay what they are. The only number I can change is the number that goes in front, which is the coefficient, the number that goes right here in front. So for this, I can see that I'm going to need I need 2 mercury oxides in order to balance the oxygens. Now I have, on this side of the equation, the product side, I have 2 mercuries, 2 Hgs, and I have 2 oxygens. Now going to the other side, I have 2 oxygens, but I only have 1 mercury. So I need to put a 2 in front of it so that I have 2 mercuries now. Now everything is balanced. So this would be the balanced chemical equation. So that's what we see here. That's what they did. They put a 2 in front of that mercury in order to balance the chemical equation. Okay? All right, let's look at water. That's a great example. H2 plus O2 produces H2O. So I want to balance this chemical equation. So first, I look at the hydrogens and they're balanced on each side. I make a list. These are the elements that are in this compound. 2 hydrogens, 2 oxygens, 2 hydrogens over here, and 1 oxygen. So everything I can see in this chart that I've made, and I would encourage you to make a chart, but in this chart that I've made, I can see that my hydrogens are balanced, but my oxygens are not balanced. Okay? So that means I need to balance the oxygens. So I have 2 oxygens right here. So to balance those, I need to put a 2 as the coefficient in front of water. Okay, well that gets rid of this, and it makes it so that I have 2 oxygens on each side, but I no longer have 2 hydrogens on each side. Now I have 4 hydrogens on this side, and I only have 2 on that side. So they are no longer balanced. But that's okay, because all I need to do is put a 2 as the coefficient in front of that H2, and now I have a balanced chemical equation. They are balanced. 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygens. So it works. That's how I would balance my chemical equation. So when I look at it this way, I can easily see that it is not, the law of conservation is not obeyed, because I have 2 hydrogens and 2 hydrogens, good, but 2 oxygens and only 1 oxygen. Where did the other one go? Where is the other one? Well, if I have an H2 and an O2, and the hydrogen breaks into H and H, so I have these 2 free because they've broken apart into 2 individual hydrogens, and I break up the oxygens into individual oxygens, okay, like this. Then these 2 hydrogens can react with this 1 oxygen to form H2O. But what am I left over with? I still have another oxygen that needs some more hydrogens, right? So in that case, I would need an extra set. I would need 2 of these, so I would need H and H in order for these to also react with this second oxygen to form 2 H2Os from this equation. 2H2 plus 1O2 to form 2 H2Os. Okay? It has to work out. You can't leave anybody out, or it's not balanced. Okay, so steps in balancing. Count the number of moles of atoms on each side. So we have reactants, we have products. Okay, so make a chart. Make your chart. Determine which elements are not balanced or do not have the same number on both sides. So the oxygen there wasn't balanced, like we said. So we balance it by putting a 2 in front of the water, right there. But that messes with everything else, so now my hydrogens aren't balanced. So I ultimately have to put a 2 in front of the hydrogens in order to finish the balancing of this equation. Okay, and this is giving an example of how that's happening. So here, balancing equation, we have an HCl and a calcium, and from that we want to form a calcium chloride. But we have 1 little hydrogen left over, and it's not able to bond with anything. So that would be incorrect. We have to have an H2 molecule. Hydrogen doesn't exist all by itself. So we have to be able to form H2 in order for this to work. So here they're showing that we start out with 2 of these, 1 calcium. And also right here, calcium, we should have calcium, it's 2 plus, so we would need Cl minus, we'd need 2 chlorines to have calcium chloride. We're missing a chlorine here as well. So that's what we show here. If we start out with 2 HCl molecules and 1 calcium, we indeed will have 2 chlorines, and we'll be able to form the hydrogen there. Okay, but chlorine doesn't exist as, or I'm sorry, hydrochloric acid doesn't exist as Cl2H2 or H2Cl2. Okay, it doesn't exist like that. It exists as HCl. So instead of changing the coefficients on the bottom, I need to change, I'm sorry, the subscripts on the bottom here, I need to change the coefficient that goes in front. Okay, so let's kind of examine this equation a little more in depth here. Okay, so we have an HCl. That's what it is. It's an HCl. plus a calcium produces calcium chloride plus H2 gas. Okay, so I want to balance it. I cannot put the subscripts here. That is not how I can balance. That's not how I balance. Okay, so that means I just have to put a 2 in front of this, and now it's a balanced chemical equation. Because now I have 2 hydrogens, 2 chlorines, 1 calcium, 2 chlorines, and 2 hydrogens. The number of everything is the same on each side of the chemical equation. So let's do a little practice here for balancing these chemical equations. Okay, so let's start out with C2H2 plus O2, and that produces carbon dioxide and water, CO2 plus H2O. So I want to make a chart. So I say there's carbon, hydrogen, and oxygen in this chemical equation. So I have 2 carbons, I have 2 hydrogens, and I have 2 oxygens. And on the other side, I have 1 carbon, 2 hydrogens, 3 oxygens. Okay, carbon dioxide plus water, I always like to think of that as 1, 2, 3. CHO, 1, 2, 3. Carbon dioxide and water. And now I need to balance it. So one word of advice that I would give is, because oxygen is all by itself here, leave it to the end. Don't balance it until you've balanced the other things. And the only other thing that needs to be balanced right now is carbon. So I put a 2 in front of the carbon. That changes my carbons to 2, but it also changes my number of oxygens. So 2 times 2 is 4, plus 1 more. That gives me 5 oxygens. Now the reason I want to leave oxygen to the end is because I can manipulate that oxygen to be any number that I want it to be. If I want it to be 5, I can make it 5. All I have to do is say, what is 5 divided by 2, which happens to be 2.5, and my coefficient here becomes 2.5. 2.5 times 2 is 5, and now this is 5, and I have a balanced chemical equation. Okay, so but you can't leave it that way. You have to change all the coefficients so that they get rid of any half numbers. So you can use a fraction as a tool to help you get to the balanced chemical equation, but in the end, the final answer needs to be multiplied by 2 so that you can get rid of the half. So I'm going to say there's 2 of these. 2.5 times 2 is 5. This is going to become 4, and this is 2. So this is my balanced chemical equation for that molecule, for that reaction, C2H2 plus O2. Okay, and that's how I would get that. All right, let's try another one here. So we have silver nitrate plus iron chloride. Okay, so silver nitrate, and what is it, iron 3 chloride, plus iron 3 chloride will produce silver chloride plus iron 3 nitrate. Okay, so that's what we have, iron 3 nitrate and silver chloride. Now I want to balance that chemical equation. So I write down all of the items that are in the equation. I have silver, I have nitrate. Now you'll notice I didn't break the nitrogen and the oxygen apart. I left them together. That's important, because by leaving them together, it allows me to simply balance nitrate as a single thing over here and a single thing over here. Okay? All right, iron and chlorine. These are the elements and compounds associated with the balancing of this. So these are my reactants, these are my products. On the reactant side, I have 1 silver, I have 1 nitrate, I have 1 iron, and I have 3 chlorines. On the other side, I have 1 silver, 1 chlorine, 1 iron, and 3, oops, sorry, not paying attention. I have 1 chlorine and 3 nitrates. Okay, so let's go ahead and see what I want to balance first. Let's start with nitrate. If I want to balance the nitrate, I see that I have 3 over here and only 1 over here. So to balance that, I need to put a 3 in front of the nitrate as the coefficient of silver nitrate. And that changes the silver coefficient to 3. It changes the nitrate coefficient to 3. And now I have to balance the silvers on the other side, okay, because they're not balanced. So I put a 3 here. That gives me 3 silvers on both sides, 3 chlorines on both sides as well. And now I have a balanced chemical equation. Everything is balanced. Okay? All right, let's see. Okay, let's try this next one. C2H6O2 plus carbon dioxide produces carbon dioxide and water. So C2H6, C2H6 plus O2 produces CO2 plus H2O. Okay, I want to balance this. I have carbon, hydrogen, and oxygen as my elements. I have reactants and products. I have 2 carbons, 6 hydrogens, 2 oxygens. On the other side, I have 1 carbon, 2 hydrogens, and 3. Once again, 1, 2, 3. Okay, I want to balance these, so I need to put a 2 in front of the carbon here. That balances those carbons, but that will change the number of oxygens. So my oxygens go from 3 to 2 times 2 is 4, plus 1 more is 5. Once again, I need 5 here. Okay. My hydrogens, I have 6. So I need to change the coefficient here to a 3 to give me 6 hydrogens. Now I have 6 hydrogens on each side of the reaction. But that changes my number of oxygens once again. 2 times 2 is 4, plus 3 is 7. So I have 7 oxygens. Once again, I have an odd number of oxygens. So to find the number that will balance those oxygens, I simply divide 7 by 2 for the other side right here. And that will give me 3.5. So 3.5 times 2 is 7. But remember, I can't keep it as a 3.5. I have to eliminate it by multiplying everything by 2. So I have 2 of these. I have 7 of these. I have 4 carbon dioxides. And I have 6 waters. Everything still remains balanced. When you multiply it by 2, it will still remain balanced. So that's the effective way to do that. All right, the last one, N2 plus H2 gives you NH3. So we have N2 plus H2 produces, NH3. N and H are the elements involved here. Okay. 2 and 2, 1 and 3. Now, a really good way to approach this is looking at the number of hydrogens, okay? So if I look at the number of hydrogens, I'll notice that I have 2 hydrogens on one side, 3 hydrogens on the other. Now if I just switch their coefficient, their subscripts as coefficients for the other, that balances them, right? So 3 times 2 is 6, 2 times 3 is 6, okay? And essentially what that's done for me is it's created a balanced chemical equation. Now, I could have looked at it a different way, okay? I could have just said, I need 2 nitrogens. That balances my nitrogens, 2. 2 times 3 here is 6 hydrogens, so I need to put a 3 here. And now I have 6 hydrogens on each side of the equation. So that's pretty simple, straightforward equation. And that's how we go about balancing things. Okay, now in this section we're going to talk about calculations using the chemical equation. So now that we can balance chemical equations, we want to be able to use that balanced chemical equation to be able to calculate the amounts of product or the amounts of reactants that we need to use to form a certain amount of product. And so this is kind of the epitome of chemistry and how we can really get down to the meat of how much of something we should use to create this amount of something else. So we're going to talk about this fact of using the chemical equation to be able to calculate these amounts. So obviously for this we need a balanced chemical equation. So that's one of the main things that we have to have. So anytime that we're going to do what we call stoichiometry, and this section that we're doing is called stoichiometry, anytime we do the stoichiometry we need a balanced chemical equation. So that's one of the first things you need to look for. Do I have a balanced chemical equation? So we need to have the chemical formulas of the reactants, the products, everything needs to be there. The equation must be balanced to obey the law of conservation of mass. And we're going to do all calculations in mole amounts. So the mole will be very important here. So here's a chemical equation. 2H2 plus O2 produces 2H2O. So if we're looking at the coefficients, this tells us that 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. So what if 4 moles of H2 react with 2 moles of O2? Well, then I would be able to, you could do that in your head, I would be able to produce 4 moles of water. And you can see that it's a 1-to-1 ratio between the H2 and the H2O if I have enough O2. Okay? So the coefficients of the balanced chemical equation, they are used to convert between moles of substances. So how many moles of O2 are needed to react with 4.26 moles of H2? So this is a little more difficult because we're not using whole numbers anymore. So we need to set this up in a way that it's going to allow us to calculate the amount of water produced from 4.26 moles of H2. Now that's assuming that we have, how many moles of oxygen do we need to react with 4.26 moles of H2 completely? So we can do this, we can figure that out because we know this, that 1 mole of O2 reacts with every 2 moles of H2. It's a conversion factor. So that conversion factor will allow us to calculate from 4.26 moles of H2 how many moles of oxygen are needed. And this is the exact way that I would set that up. 4.26 moles of H2 times my conversion factor, 1 mole of O2. I'm converting to O2. Now remember, whenever we do a conversion, we always start with what we're given. So here, we're given the amount 4.26 moles of H2. So that's what we start with. And then we go to the thing that we're trying to get to, which is moles of O2. So from H2 to O2. And this is where stoichiometry comes into play. Stoichiometry is the ability or the process to be able to go from one thing to a new thing. So if I wanted to go, so I can go from H2 to O2 like we've done here, or I could go from H2 to H2O. So either way, I can use the conversion factors that are given to me. So from H2 to H2O, it would be 2H2O for every 2H2. And I would use that conversion factor instead. And I would still start with 4.26 moles of H2. This is moles, and this is moles of H2O. So the process would be exactly the same, but I'm going to get to a different item. Rather than getting to H2, I'm getting to H2O. Okay, and that's the heart of stoichiometry. The heart of stoichiometry is being able to convert from the moles of one thing to the moles of a different thing. And we have to have a balanced chemical equation to be able to do that, because the balanced chemical equation is where the relationships between these molecules is shown. Okay? So here we have now moles to grams. So to go from moles to grams, we've done that. We've done the conversions for those. We need to use the periodic table and find the gram amount masses from the periodic table to do those conversions. So that's nothing new. So convert 1 mole of O2 to grams. The path is moles of oxygen to grams of oxygen. Okay? And then we're going to find the molar mass of oxygen. 32 grams of O2 equals 1 mole of O2. That's our conversion factor. Okay? Obviously. So just like we would do for anything else, 1 mole of O2, I'm going to convert it to the grams of O2 from the moles of O2. So there's 32 grams in every 1 mole. Okay? So 1 mole of oxygen equals 32 grams of oxygen, which seems kind of obvious, but the process is what's important here. I could make that number 1 anything. I could make it 8.75 moles of O2, and the process would be the same. 32 grams of O2 for every 1 mole of O2, and that will allow me to convert, once again, to the grams of O2. Okay? Now, when we're considering the conversion of mole reactants to mole products, okay, we're going to look at another example here. So we have to have a balanced chemical equation. We can see that we do have a balanced chemical equation here. 1 mole of C3H8 results in 5 moles of O2 consumed, and 1 mole of C3H8 over 5 moles of O2. Okay, so these are the conversion factors. 5 moles of O2 for 3 moles of carbon dioxide. 3 moles of carbon dioxide for 4 moles of water. 1 mole of C3H8 for 5 moles of oxygen. So as you can see, these are all conversion factors. I can go from, so with this, I can convert from C3H8 to O2. Or I can convert from O2 to CO2. Or from CO2 to H2O. Okay, so there's a bunch of different available conversions that I can do using this balanced chemical equation. So here we're saying calculate the grams of oxygen reacting with 1 mole of C3H8. So this is a simple process of going from the moles of C3H8 to the moles of oxygen and then to the grams of oxygen. So this is the stoichiometry part, converting from C3H8 to oxygen. So that's our first step. So we have 1 mole of C3H8, 1 mole of C3H8, and I want to convert that to the moles of oxygen. So I need my balanced chemical equation. That's where the quantities for that come from. So I'm going from C3H8 to O2, and that's 1 mole of this for every 5 moles of O2. So that's what I'm going to put here. Moles of C3H8 go on the bottom here. Okay, they cancel. I have 1 mole of that for every 5 moles of this. So 5 moles of O2. Now using that 5 moles of O2, I can answer the question. The question is, how many grams of oxygen reacts with 1 mole of C3H8? So 5 moles of O2, we already did oxygen. O2 weighs 32 grams per mole, okay, as calculated from the periodic table. So we're going to say 5 moles of O2, and we're going to go to the grams of O2 from the moles of O2, and there's 32 grams for every 1 mole. So we would say 5 times 32, that's how we would get to these numbers, okay? We would say 32, 5 times 32, and we would get 160, that's 160 grams of oxygen is needed to react with 1 mole of C3H8. Okay, so this is how we would be doing this. All right, so now we're going to continue, but we're going to talk now about calculating the grams of products from moles of reactants. So the grams of CO2 from the combustion of 1 moles of C3H8. So how would we do that? So we have 1 mole of C3H8 again, and now we want to find the grams of CO2. So once again, the moles of C3H8 to the moles of CO2, and then we're going to convert to the grams of CO2. It's really nice if you plot it out like this, like we're saying at first, right here. Okay, just plot it out. This is the stoichiometry part. The stoichiometry is going from C3H8 to CO2, and you can only do that in moles. So we have 1 mole of C3H8, 1 mole of C3H8, and we want to go to the moles of CO2 from the moles of C3H8. Now, where does that relationship come from? It comes from the balanced chemical equation up here. So we need to look at the moles of C3H8, which are 1, and the moles of CO2, which are 3. And that's how we're going to do this. So the moles of C3H8 are 1, and the moles of CO2 were 3. So we're going to produce 3 moles of carbon dioxide during this reaction. Now, how many grams of carbon dioxide did we produce? Well, that's just a simple conversion of moles of CO2 to the grams of CO2, okay, from the moles of CO2. So carbon has a mass of 12.01 grams. O2 we know is 32 grams. So we have 32 plus 12, and we get 44. This is 44 grams per mole. Okay, we're not going to really worry about that, 0.01. But we have 44 grams of CO2 for every 1 mole of it. So we have 3 times 44 gives us 132 grams of carbon dioxide. That's the amount of carbon dioxide that would be produced in mass from 1 mole of C3H8, which is 3 moles of carbon dioxide. So knowing the path is really important. So I need to answer the question. This is the first question I need to answer, moles to moles, the stoichiometry. Okay? Now, a lot of times they don't give us the mole amounts, they give us the grams. This is how much you start with in mass, in grams. 36 grams of water. And then they want you to find out how many grams of something else was required to get there, or did you produce. So in this case, we're going to go from grams of water to the moles of water. And then from the moles of water, we're going to go to the moles of the other thing. This is the stoichiometry part. The stoichiometry part being converting from the moles of one thing to the moles of another thing. Now, I can't do that mole conversion unless it's in moles. So that's why I have to go from the grams of water to the moles of water. That's my first step. So grams of H2O, and I know how much I'm starting with. It's 36 grams of water, 36 grams of water. And I'm going to convert that to the moles of water from the grams of water. Okay? So now water has a mass of H2 and O. This is 16 and this is 2. So that's 18 grams per mole. So we have 18 grams here in 1 mole. So 36 divided by 18 would be 2 equals 2 moles of water. Okay, so if I had produced 2 moles of water, how many moles, so that's the next question, from 2 moles of water, how many moles of C3H8 were required to react to produce it. So we're going to start, this is the stoichiometry part, 2 moles of water, and I'm going to convert that to the moles of C3H8 from the moles of water. And I go back to my chemical equation up here, and we can see that there's 4 moles of water for every 1 C3H8. So that's the conversion I need to use. 1 mole of C3H8 for every 4 moles of water. So we have 2 divided by 4 equals 0.5 moles of C3H8. So half of a mole of C3H8 will produce 2 moles of water. Now, I haven't answered the question. Calculate the grams of C3H8. I am in the moles of C3H8. Well, it's now just a simple process of converting from moles of C3H8 to the grams of C3H8 from the moles of C3H8. So now I need the mass of C3H8. So we have C3H8. So 12 times 3 is 36 plus 8 more. And we get 44 grams per mole for C3H8. So this is 44 grams for every 1 mole of C3H8. Okay, so that's the process. So now I take 0.5 times 44, and I get 22 grams of C3H8 will react to produce 36 grams of water. Okay, so here we go. We have 22 grams of C3H8. All right, so that's the epitome of what we're going to do. Go from the grams of one thing to the grams of another thing, but not forgetting this is the stoichiometry step, mole to mole conversion. And that comes from, those conversion factors for the mole to mole conversions come from our balanced chemical equation. Okay. So here we want to calculate a quantity of a reactant. Okay. So calcium hydroxide neutralizes HCl. Calculate grams of HCl neutralized by 0.5 moles of calcium hydroxide. So we're starting with the moles of calcium hydroxide, which means that we can easily do the stoichiometry step without having to convert to moles first because it's already in moles. So we can take that 0.5 moles of calcium hydroxide and we can convert it to the moles of HCl. So here we see that 1 mole of calcium hydroxide will react with 2 moles of HCl to produce 1 mole of calcium chloride and 2 moles of water. And ultimately we want to find the grams of HCl that are going to react with that 0.5 moles of calcium hydroxide. So that's the path. Our very first step is to take the 0.5 moles of calcium hydroxide and convert it to the moles of HCl from the moles of calcium hydroxide. Okay, and we know there's 2 moles of HCl for every 1 mole of calcium hydroxide according to the chemical equation here. So 0.5 times 2 would give us 1 mole of HCl. So we would produce 1 mole of HCl. Now, how much is that in grams? Well, I simply do the mole to gram conversion. Grams of HCl. So we have, for every 1 mole of HCl, we have H equals 1 and chlorine equals 35.5 grams. So this is 36.5 grams per mole of HCl. So we're going to make 36.5 grams of HCl, or we're going to need 36.5 grams of HCl to react with 0.5 moles of calcium hydroxide. Okay, so that's how much we would need, 36.5 grams of HCl. Okay, so here we're just seeing a visual of that. Here's our solid calcium hydroxide, and 147 grams of, we have 1 mole of it, which is 147 grams of reactant. And we need that to react with 2 moles of HCl. 2 moles of HCl is 73 grams. So you need 74 grams to react perfectly with 73 grams of HCl to produce 11 grams of this and 36 grams of that. Okay, so the hopefully we've seen those strategies, and I don't want to muddle up the process here, but you can do them all in one step. But I really recommend trying to understand the process. It's the mole to mole process is the stoichiometry part, where you have to use the balanced chemical equation. Okay, so here this is an unbalanced chemical equation, so they need to balance it, so we balance it, and now we have a balanced chemical equation. And using that balanced chemical equation, they're saying calculate the moles of Cl2 reacting with 5 moles of sodium. So remember, you have to make sure your equation is balanced, or else it's not going to work. So we're going to take 5 moles of sodium, because that's what they gave us to start with, and we want to calculate the moles of Cl2. So this is just a simple stoichiometry step where I'm going to go from the moles of sodium to the moles of Cl2, from the moles of sodium. Okay, and looking at my balanced chemical equation, there's 2 moles of sodium for every 1 mole of Cl2. 2 moles of chlorine, I'm doing that wrong. So there's 2 moles of sodium for every 1 mole of Cl2. So here I'm going to say 5 divided by 2, and I'm going to get equals 2.5 moles of Cl2. Okay, but the question is asking, okay, well that is the question. So calculate the number of moles of Cl2. That's what we did. There's 2.5 moles of Cl2. Calculate the grams of sodium chloride produced when 5 moles of sodium react with excess chlorine. Whenever it says excess, all that means is that it's more than enough reactant, so you don't have to worry about it. You don't have to, it's not part of the question, in other words, when it says excess. The thing that's part of the question is this one, the 5 moles of sodium. So 5 moles of sodium, once again, 5 moles of sodium. How many moles of sodium chloride are produced from the moles of sodium? And this one is a 2 to 2, so it simply makes 5 moles of sodium chloride. Now, the question though wants us to find the grams of sodium chloride. So now we need to take those 5 moles of sodium chloride, and we need to convert it to the grams of sodium chloride from the moles of sodium chloride. So I have 1 mole of sodium chloride, and the grams, I need to say sodium has a mass of 23, chlorine has a mass of 35.5, and we get 58.5 grams of sodium chloride for every 1 mole of it. So 5 times 58.5, that would give us 292.5 grams of sodium chloride from 5 moles of sodium. So 5 moles of sodium will produce 292.5 grams of sodium chloride. Okay, now one of the final concepts that we're going to try to understand is that of theoretical and percent yield. So what we have been doing are theoretical yields. These are calculated yields. They're yields that are produced because because we calculate them, not because that's how much we actually have made in the laboratory. Okay? The actual yield is the amount produced when the reaction is actually performed. So I go into the laboratory, I do the reaction, and I produce a very specific amount. That will never be the same as the theoretical yield. The theoretical yield is always the perfect reaction, and we never run perfect reactions in the laboratory. So here I have theoretically said we should produce 292.5 grams of sodium chloride. But when I go and run that reaction, I only produce 287.3 grams of sodium chloride, which would be practical because I'm never going to do everything so perfectly or collect all the mass so perfectly that I'm going to get everything. There's always going to be an amount that is lost during the reaction and during the handling of that reaction. So that's why we calculate things called percent yields. The percent yields allow us to calculate how much, how well you actually did the reaction compared to what you should have accomplished. And a percent yield is simply equal to the actual yield that you find in the laboratory divided by your theoretical yield that you calculated and then multiply it by 100. So here's an example where you should have, theoretically, you should have made 132 grams of carbon dioxide. Well, the actual yield was only 125 grams of carbon dioxide. So I take 125 divided by 132, I multiply by 100, and I have a 97.4% yield, which is a very great yield. It would be very hard to actually get a 97.4% yield. That would be very difficult. Okay, so let's try some practice questions here. If the theoretical yield of iron was 30 grams and the actual yield was 25 grams, calculate the percent yield. So actual percent yield equals actual over theoretical times 100. Okay, so we have 30 grams over, oops, I'm sorry, that's the theoretical. That should be on the bottom. So we have 25 grams over 30 grams times 100. Okay, so 25 divided by 30 times 100, and we get 83.3% yield. So that's our percent yield, 83.3. Okay, 83.3%. Calculate the percent yield if 26.8 grams of iron was collected in the same reaction. So we just simply say 26.8 grams divided by 30.0 grams. The theoretical doesn't change, it's just the actual that changed. So we're going to say 26.8 divided by 30.0 times 100. Now we have an 89.3% yield. Our yield had increased. Okay? All right. So let me do a few more examples here. So let's take our water example. So H2 plus O2 produces H2O. And we're going to introduce one other concept called the limiting reactant. Okay? So this is an unbalanced chemical equation, so I need to balance it. So to balance this chemical equation, I need 2 waters to balance the oxygens, and then I need another 2 hydrogens to balance the hydrogens in the water. Okay, now I have a balanced chemical equation. So let's say that with this balanced chemical equation, I told you you have 15 grams, oh no, that's not, you have 3 grams of hydrogen and you have 15 grams of oxygen. And then I asked you, so which one of these is going to run out first? Which of those is going to run out and go to 0 while there's still some left over of the other one? So this is that idea of having excess reactant or product. So the way that I would determine that is I would simply set these things to each other. I would say how many grams of hydrogen, if I have 3 grams of hydrogen, how many grams of oxygen will react with that? And that's going to tell me if I have enough oxygen or if I don't. So here I'm going to start with the grams of hydrogen, 3 grams of H2. And I'm going to convert that to the moles of H2 because I can't do anything with it until it's in the moles from the grams of H2. So there's 1 mole for every 2 grams. So 3 divided by 2, and I get 1.5 grams, or sorry, 1.5 moles of H2. Okay, so now that I have 1.5 moles of H2, I can use that to convert to the moles of the other thing, which is the moles of O2, from the moles of H2. And they have 2 moles of H2 for every 1 mole of O2, so 1.5 divided by 2, and I get 0.75 moles of O2 are produced, or are needed. Well, how many grams is that? 0.75 moles of O2, and I'm going to convert it to the grams of O2 from the moles of O2. There's 32 grams for every 1 mole. So 0.75 times 32 equals 24 grams of O2. So if I have 3 grams of hydrogen, I would need 24 grams of oxygen. I don't have that much oxygen. So that means this 15 grams of oxygen is the thing that it will run out first during this reaction. I will have H2O left over. So what does that mean about how much water I will produce? Well, that means that this oxygen is the determining factor for the amount of water that will be produced in this reaction, because it will go to 0 and then the reaction will stop, and there will be hydrogen left over. All the oxygen will be gone, and then as much water as I could produce will have been produced. So if I want to know the theoretical yield of water that I produced from 3 grams of H2 and 15 grams of oxygen, the first thing I had to do was find out which one is going to run out first, and that was determined to be the oxygen. And then I would use that one, 15 grams of O2, and I would convert it to the grams of the moles of O2 from the grams of O2, so that I can do the stoichiometry of it. So there are 32 grams for every 1 mole, so 15 divided by 32, and I get equals 0.46875 moles. Now I can convert that from the moles of O2 to the moles of H2O using my balanced chemical equation. Okay, so my balanced chemical equation tells me there's 1 mole of O2 for every 2 moles of water. 1 of O2 for every 2 of water. So 0.46875 times 2, and I get to 0.9375 moles of H2O. Now, how many grams of H2O is that? So I'm going to take that 0.9375 moles of H2O, and I'm going to convert it to the grams of H2O from the moles of H2O. So there are 18 grams for every 1 mole, as we determined earlier for the water. So I'm going to take that 0.9375 and I'm going to multiply it by 18, and it comes out to be 16.875 grams of H2O. And probably to, you wouldn't need that many numbers if we were actually doing the significant digits, which I didn't really include significant digits into these numbers here. So that's why we're not really taking them. Okay, so that's how I would find the amount of water that was produced from this reaction. And what we call this thing that runs out first, we call that a limiting reactant. And this one is in excess. Okay? And the limiting reactant tells us how much water we produce. So if the question said, from 3 grams of H2 and 15 grams of O2, how much water is produced, we would know that we need to find out which one of these runs out first so that we could use that one to go here. Because this one would give us a number that was too big. We wouldn't actually produce that much H2O because this is the one that is the determining factor. The O2 is the determining factor, not the H2. Okay, this one does not determine it. It is this one that does.